So this is question 8 of the paper 2 higher tier sample assessment materials for Edexcel GCSE physics. We're getting towards the end of the paper, so it is getting quite hard. The chart, so we've got here, figure 23 shows an electric car connected to a battery charger. The car has a rechargeable battery to drive its motor. The rechargeable battery provides a potential difference of 330 volts and can store up to 64 megajoules. It takes 8 hours for the battery to receive a full charge. Assume that the charging process is 100% efficient. Calculate the total charge that flows while the battery is being charged. Now, I went about this in completely the wrong way. It still works. A really complex and convoluted way, because I forgot about one equation that exists that we can use to help us here. So let's think about what I've got. I've got a voltage, and 64 megajoules is an energy. 8 hours is a time, and we've got that it's 100% efficient. And they want us to work out a charge, which is Q. Now, do you know an equation that involves 3 of these 4 letters? Chances are you've forgotten it, because this is the equation that everyone at GCSE and A-level physics likes to forget, and it is the definition of voltage. Voltage is energy transferred per charge. So we can use this equation, V equals E over Q, to help us rearrange it in terms of Q. Q is going to equal energy over voltage. The energy, I'm told, is 64 megajoules. Mega means times 10 to the 6, or means a million. And divide that by the voltage of 330. And then Q comes out as 19399 point many coulombs. I wouldn't want to write that down. So what you should do in this circumstance is press eng on your calculator. I've lost my calculator. Let me just do this sum and you can see it. So 64 times 10 to the 6 divided by 330 comes out with this number. If I click, let me see if I can see it a bit easier. It's not very bright today. There we go. If I press eng, then it automatically goes into it's not standard form, but it's a times 10 to the form. And it comes out as 193.9. So I'm going to write equals 194 times 10 to the 3 coulombs. Much easier to read for your examiner. Then, calculate the average charging current. So the charging current, I'm going to use the definition for current, which is that current equals charge over time. So you do need to use your answer from the last part of the question. So I'm going to use the non-rounded version, 193,939, sorry, a bit of a blank then on the numbers, divided by the time, and I'm told here that it takes 8 hours. So 8 hours is 8 times 60 minutes. Times 60 seconds, don't forget that second 60, another thing that I did before, and it comes out as 6.7 amps, which seems pretty sensible. So 2 equations that we often forget to use because they're more rare than the other ones. Then we hit our first 6 marker, and this is a bit of a tricky one. Once you get your head around it, it's not terrible, but trying to read understand what it says is quite hard. So the battery charger shown in figure 23 is connected to the 230 volt AC domestic mains supply. The output voltage of the charger is 330 volts and it provides DC charging current. Charging stops if the charging current exceeds 15 amps. Explain how electrical components in the charger can be connected together to give this type of output. So what can we use to make 230 volts AC into 335 DC that stops at 15 amps, and how do we connect them? So you're looking for 3 components here, okay? Now the first thing we need to do, firstly, we need to increase the voltage from 230 volts to 335 volts, and to do that we use, I'm going to straighten my paper, by using a step-up transformer. And I'm going to say that means more coils on the secondary side. Now I'm going to struggle over here. Remember a transformer, we've got a coil on one side, the primary coil, and then we've got a coil on the other side, a secondary coil, usually with an iron core. And these 2 coils aren't connected at all. So here we're going to have the main supply, and on this side we're going to have the rest of the circuit. So this is now, we call it a secondary circuit. Well, that's not really something you cover at GCSE, but they're mentioning it in the mark scheme. And this is the primary circuit. You might talk about the secondary coil. So we've taken the electricity and put it into a secondary circuit where we've increased the voltage. So in the secondary circuit, we need to add some things in. Now, to start with, we need to make the AC DC. So we're going to add a diode in series because we want all the current to go through it to change AC to DC, because diodes only allow current through in one direction. So now, instead of the AC that would look like this, we're going to get a DC that looks like this. It's only in one direction, so it counts as the DC. In reality, they would then whack a capacitor in there and make this into a smoothing circuit, so you wouldn't get such a jump. But GCSE, we're just going to use the diode. So we're going to add a diode in series to change AC to DC, and then it needs to stop if the current exceeds 15 amps. So we also need to add a fuse into the secondary circuit, once again in series, because we want the current to go through it. The fuse should have a rating of 15 amps, so it will melt for anything over that. And break the circuit. So I think that would get you all the marks, but you can also say alternatively, add in a circuit breaker instead of the fuse, as this would not need to be replaced. If current exceeded 15 amps, just switch back on. So circuit breakers, my hand's hurting now. Circuit breakers, they're like reusable fuses. Fuses melt and you have to actually change them if they go, but a circuit breaker, you can just flip the switch. That's probably what you've got in your house. If your electricity goes, someone goes and flicks a switch, it just brings it back. So it's not a terrible question when you get your head around it, but it's not that nice to start with.